Okay, thanks for Hongyin and welcome everybody. And this is Mingxin here. And today I'm going to talk about Squirrel, automating attack analysis on blockchain incentive mechanisms with deep reinforcement learning. So this is a joint work with Carnegie Mellon University, Cornell Tech, and Stanford. And we are advised by Professor Julia Fancy and Professor Eric Juice, and we are cooperating with some of the very talented PhD students. So before the beginning, I want to say that this talk will mainly focus on blockchain security issue. And since we are not experts, I know that there are a lot of the audience are very knowledgeable in this field. So any comments will be really helpful. So blockchain in short is this decentralized ledger. And this basically stores some very important data like your account, right? So you want to ensure your data is secure. So you need a consensus algorithm. And there are two main goals of the consensus algorithm. The first thing is consistency, that your data should be correct between the distributed node. And it should be liveness. It should have liveness that your consensus algorithm won't stuck in somewhere. And most of the consensus algorithm will make a very basic assumption that the majority of your participants are honest. To ensure that, in practice, you need some incentive mechanism. And incentive mechanism basically says how you assign your reward to the participant, and you encourage the honest behaviors. Well, we know that it's really important, and actually people are really care about this because there are $1 billion of money related to the incentive mechanisms. However, they are susceptible to attacks. In 2014, some researchers proposed the very famous incentive mechanism attack called selfish mining attack, and it claimed that 25% of the attacker can control or amplify its reward. And there are a lot of following papers, and researchers propose some other kind of attack, basically amplifying the attacker's reward. And nowadays people are proposing new protocols very frequently, and they're using new incentive mechanisms. However, there are very limited theoretical analysis. Sometimes it propose their incentive mechanisms form some Nash equilibrium, but we think that most of the theoretical analysis is a little bit vague. And in this talk, I'm going to introduce Squirrel. We are trying to propose a somehow general framework to analyze the incentive mechanism. So the outline of this talk will be like I will first introduce our sanity check. We recover some known attacks strategy, and we will show some case study. So there are some new results, and finally I will show a very important result that we identify a new attack on the Casper FFG protocol when the miners collude with the voters. So the background, the most simple incentive mechanism in blockchain is the Bitcoin's incentive mechanism, and it basically says like when the miner mines a block in the longest chain, well, it gets the reward. And if your block doesn't belong to the longest chain, you don't get reward, just like this. And the 2014 paper proposed the selfish mining attack, and it basically says the attacker first mines a block, but it doesn't publish it immediately, and it hides it. When some other honest party mines a block, the attacker immediately publish its hidden block, and then the honest block get override. Then the attacker can gain the reward while the miner waste their effort. In such case, the attacker can amplify its reward. So nowadays, the researcher modeled the system as a Markov decision process, and they modeled the agent trying to maximize the reward in a randomized environment, especially in the blockchain environment. And well, MTP, we all know that it can be solved exactly with MTP solvers, some traditional one like policy iteration, value iteration, but they have their intrinsic drawbacks. You have to represent the state, transitions, reward policy as matrices. And the dimension grows very quickly. And it grows quadratically to your state-based size. So it brings up two main problems. It's very difficult to handle large or continuous state space, and it's not applicable in non-stationary settings, something like Markov games, multiple agents, something like that. And DRL is a very powerful tool in dealing with those problems. It basically represents the value mapping as a deep neural network instead of table, so you don't have to worry about the dimension disaster. And we can design the environment that does not require a full specification of state-based transition. So also you don't need to worry about write down every transition very, very carefully. So this is our system. It's very classical reinforcement learning framework. We have our RI algorithm and we have our environment. So in the environment part, you basically extract some feature from your protocol, especially your incentive mechanism. For example, in Bitcoin, well, we extract some state base, we define some action space, and we define some rewards, and we determine the transition by random mining. Well, this is all consistent with the existing literature. For the RI algorithm, well, you have some single agent algorithm and you have some multi-agent algorithm, depends on what you are trying to do. And actually, you can use whatever algorithm you like. You can use something like DDQN, SAC, A3C, PPO, whatever. And here we are comparing to some baselines. The first baseline is the honest mining, which is the honest behavior. And the second thing is the 2014 selfish mining paper, the SM1 strategy. And the third one is, well, some researcher proposed the optimal selfish mining. They solve the MTP and they get the so-called optimal selfish mining strategy. So the first thing is we recover the so-called optimal selfish mining within a very, very close margin. As you can see here, well, the performance of our strategy can approximate the reward within less than 1%. So this is really good. And let's move on to our first case. Well, in practice, we realize that the attacker's hash power isn't fixed. And the total hash power is changing very frequently and quickly in the real environment. And it's not very predictable. So you don't have a very good way to use the traditional MTP solver to get the optimal strategy here. Therefore, we train our agent in using a predefined random process, and it learns to behave in such a dynamic environment. And we compare it to other attacking strategies. And we crawl some real data and form a time series, and we test our squirrel agent under this environment. So the final result is that our squirrel agent behaved the best among all those attacking strategies, which shows our algorithm can be useful in practice. The second case is that, well, it's very natural to think that there are multiple agents are competing with each other. For example, you have one agent and one honest agent, one OSM agent, which means it's using a fixed optimal selfish mining strategy. And there is another agent trying to do whatever it wants. Well, we run some experiments, but we see the curve is really weird. And why are the curves is not smooth, and why does the deep reinforcement learning performance is worse than the honest? Well, there is some reason. We discover a widely adopted model, so-called rushing adversary, in studying of multi-agent attacking behavior is a little bit weird. So it basically says one honest victim will act as the background of the environment, and there are multiple competing attackers at either following some fixed attacking strategies, or they are adaptively improving the attacking strategy. Well, what's the problem with it? A little bit counterintuitive phenomenon here, that rushing adversary do not always give an agent more power in multi-agent setting with incomplete information. What does that mean? Well, just check out this very simple example. So here, well, you have 3 agents competing with each other, and there's an honest agent, and there's a blue guy who is trying to minimize the winning vote, and the yellow one is trying to maximize the winning vote. Well, obviously, if they can see how honest agents perform, then obviously the blue guy is trying to revert the honest vote, and the yellow one is trying to, vote the same as the honest player. Well, in this game, they choose such a strategy, and the maximum of the winning vote will always be 2. However, in non-rushing setting, that those 2 attackers cannot see how the honest agent perform, then they can do nothing but to guess, and they can only random guess, right? So there is some possibility that they guess all the same vote, so the expected reward is actually higher than non-rushing setting. So we see here that the yellow one is the yellow guy have less information than the rushing setting, but it gains more reward. So the conclusion is rushing adversary doesn't always give you a better performance in multi-agent environment. So we try to propose a time segmentation model to solve this problem. I'm not going to describe the detail of it. So the final result is like that, and we train our agents in such an environment that there is an honest agent, 1 optimal self-mining agent, and 1 strategic agent. And our squirrel agent can do much better than if you are simply plug in the optimal self-mining agent here. So what does this mean? Well, rushing adversaries are natural in the single agent setting, and we need to think very carefully about how to implement worst case adversaries in Markov games with incomplete information. And this conclusion is not very specific to blockchains, and it actually can raise some problems in other fields. I mean, in the security issue. So the third case study, well, it's also very natural to think, what if we train 3 reinforcement learning agents at the same time, or we train more than 3, something like that. And we show that when there's only 2 squirrel agents competing with each other, well, this is all in our time segmentation model. And actually, we can observe some amplification of the reward in the 2 squirrel agent case. But when we get into the 3 squirrel agent case, we cannot observe any kind of amplification of the reward. And we look at the training process, and we realize that in between epoch of around 90, the agent to deviate from the honest strategy. And actually, we observe that its reward just goes down, and the other 2 agents can gain more in such case. So we just show that you can use reinforcement learning to somehow give you some insight of the natural equilibrium. So here we propose a very simple conjecture that honest mining is actually a natural equilibrium for more than 3 strategic agents. Well, this is not a rigorous thing, and we are looking at it from a very empirical perspective. So finally, we discover an attack in the Casper, the friendly finality gadget, the protocol that is currently used in the Ethereum protocol. So what is Casper FFG? Well, the underlying block generation protocol is the same as the original one, the proof of work one, but Casper FFG allows some player to deposit their money in a validator pool, and they can vote for a checkpoint for every 50 blocks. For example, here they can vote for, and for every checkpoint height, the validator can only vote for 1 checkpoint. For example, in this case, we see that, well, actually the red one and the yellow one combines, they get more than 2/3 of the vote. So the B2 get justified. And here we refer to the vote, the weight of the vote as their deposit. When 2 consecutive checkpoints get justified, the previous one get finalized. And if 1 block get finalized, it remains in the main chain forever, and every chain doesn't include this block will be considered invalid. And how does Casper FFG protect against misbehavior? First thing is that you can't vote for 2 contradict checkpoints at the same height. And if you vote for some contradict checkpoint, your deposit will get slashed and you lose a lot. Secondly, if we want all the voters vote for the same checkpoint. So if some voter is voting on a checkpoint different from the justified one, its deposit gets shrink a little bit. And if you vote for the correct checkpoint, your deposit will get a little bit amplified. So you get some reward here. And this is very natural. And the original paper of the Casper FFG claims that if each individual validator has less than 1/3 of the total deposits, the honest behavior is actually a natural equilibrium. However, it's not, when you consider the voter can collude with the miner, then the adversary can do much more. It can combine some attack like selfish mining attack and the voting attack. And it can decide which blocks to build on. It can decide which block to vote, and it can decide when to release its blocks and votes. And actually the state base is larger, and it's a little bit too large for the traditional MTPs. So we train our agents, and we design the environments, and we use a very traditional, I believe that is the DTQN reinforcement learning algorithm. And we learn some kind of attacking strategies. Well, the strategy is a little bit complicated, but the high level idea is very simple. So I'm going to explain here. So at this, it's very similar that the attacker first mines some block, but it doesn't publish it immediately. And when somebody else mines a checkpoint block, some validator will vote for this checkpoint block, right? And after it observes some of the validator vote for the checkpoint, it releases its own checkpoint, and it votes for its checkpoint immediately. Well, in this case, the longest chain is actually the attacker's chain. So according to the honest behavior, the yellow validator should vote for the attacker's chain, attacker's checkpoint. Therefore, attacker's checkpoint got justified, and therefore the attacker and the yellow validator get some reward, while the blue validator gets some penalty. So well, the actual attack strategy should consider very carefully about its releasing timing, something like that. So and actually we show our squirrel strategy can do much better than all other attacking strategy, and we compare the field baselines here, and we even show that in the worst case, the attacker can amplify its reward by 30% more. So this is really bad. And here we got some other results. Well, we are running out of time, so I'm going to skip a little bit. So we do some more experiments on Ethereum's protocol, and we discovered that the Ethereum's uncle block mechanism is also susceptible to attack, and also we recover natural equilibrium in the block withholding games. Well, it's a totally different setting, but it shows our reinforcement learning agent is powerful in some game setting. So finally, here are some take-home messages. First thing is, deep reinforcement learning can be a very useful tool for analyzing complex incentive mechanisms, especially in large or continuous state-based and non-stationary environments, especially for the new incentive mechanism in blockchain system, because they are much more complex than the original Bitcoin one. And secondly, the notion of a rushing adversary should be revisited for multi-agent games. That's the phenomenon we observe in our, when we do some research in our paper. And thirdly, we need to think very carefully about the composability of incentive mechanisms. As you can see, you may have a incentive compatible mechanism, but when your mechanism is a subsystem for a whole system, then you really have to carefully think about the composability, because when it combines with other part of your system, you might have a non-incentive compatible mechanism, just like what we observed in the Casper FFG thing. And finally, you have to think very carefully about relative incentive compatible mechanism. That means the attacker can deviate from honest behavior. It can lose a little bit, but it causes very big harm to the whole network. So some other participants will leave the network, and the attacker can gradually gain more power in the network, and then finally cross the security threshold. So your network is broke. Therefore, we gotta also think about relative incentive compatible mechanism in blockchain system design. Well, that's all. Thank you for coming here. If you have any questions, you can ask directly.
Okay, thank you, Min-Xun. It's a great talk. We'll collect some questions from your audience. My first question, when the Nash equilibrium is considered, are there some results about the price of anarchy? Maybe some learning results or theoretical results?
Well, it's very difficult to consider market price. I've seen some papers discussing about the market price, but since market price is really a little bit independent from your system design, so basically all of the analysis paper will focus on the system itself, not considering the market price. So, and well, we can actually take the time series of the market price as a time series data and plug in some machine learning techniques to boost our reinforcement learning agent. Well, that is a direction, but it's a little bit difficult to do so.
Okay. And second question, can you briefly introduce some highlight results about self-mining? Is there a better way to resist self-mining?
So you mean how to prevent selfish mining,
So
right?
many, yes.
So, well, there's multiple ways to do so. So the first thing is you change your game and you transform your game as a competitive game into a cooperative game. So if somebody else is wasting others' effort, it will lose a lot. So it's one direction that you design your game as a cooperative game. So you don't have to worry about selfish mind. And the other thing is you can't override others' vote or block or something like that. So you don't have to, the core of the selfish mining is to waste others' effort. So this is another direction. For example, fruit chain does so. And well, the other thing is you can use a totally different mechanism. For example, you can use a committee to vote, something like that. For example, the EOS, something like that. So, well, it's a totally different topic. They don't have to worry about selfish mining, but they have to worry about some other security issues.
Okay. Thank you, Minxun. It's a great talk.
Okay.
Okay, we can end our talk now, and next talk will start at 7 o'clock.